11. March 1997. Bituminization Demonstration Facility, Tokai Reprocessing Plant, Tokai Mura, Ibaraki Prefecture. At 10:06 in the morning, in a low-level radioactive waste building at PNC Tokai Works, a 180-litre drum being filled with molten bitumen and reprocessing waste caught fire. The operation was classed as routine conditioning, liquid waste from the Tokai Reprocessing Plant, containing cesium, strontium, ruthenium, plutonium, and other transuranics, was supposed to emerge as a stable, solid drum destined for storage. Fire was not part of the design basis. Operators extinguished visible flames within about 1 minute using a water spray. Ventilation was reduced to keep smoke from spreading through the building. On paper, safety analysis assumed negative pressure and filtration would confine activity even in an upset. In practice, hot drums, residual reactions, and a closed filling room allowed flammable gases to accumulate for nearly 10 hours. At 8 o'clock that evening, those gases ignited. The explosion would damage the facility, expose 37 workers to internal contamination, and be officially described as Japan's worst nuclear accident to date. The way the numbers emerged would alter how the country saw its nuclear program. A Science and Technology Agency clerk in Tokyo receives a routine morning stack of reports on 11 March 1997. Reactor status updates, radiation monitoring summaries, and ongoing discussions about the 1995 Monju sodium leak. No one yet mentions Tokai's bituminization building. The quiet morning reflects an institution still navigating public distrust after earlier controversies. Video editing, delayed notifications, and institutional opacity that had already damaged confidence in the Power Reactor and Nuclear Fuel Development Corporation. Tokai Mura sits 110 to 140 kilometers northeast of Tokyo. For more than 30 years, this nuclear village has hosted Japan's early experimental reactors, the Tokai Nuclear Power Plant, the country's first commercial unit, and the Tokai Reprocessing Plant. The reprocessing facility, designed to handle approximately 0.7 tons of heavy metal per day of oxide fuel, represents a critical node in Japan's fuel cycle vision. The Purex process extracts uranium and plutonium, generating high-level, intermediate-level, and low-level liquid wastes. Each stream requires treatment before storage or disposal. The bituminization demonstration facility stands at what operators consider the safe end of the cycle. Here, low-level aqueous wastes, rich in sodium nitrate and phosphate containing fission products and actinides, are mixed with molten asphalt to produce solid drums suitable for long-term storage. On paper, this is mature, low-risk technology. Public discourse about nuclear accident conjures images of reactor cores and criticality hazards. Few imagine that a low-level wasteline could produce Japan's worst nuclear event to date. The institutional architecture shapes expectations. The Science and Technology Agency serves as central regulator and parent ministry for PNC. The Nuclear Safety Commission provides advisory and oversight functions. PNC itself operates reprocessing and bituminization facilities under government backing, expected to deliver on fuel cycle promises in a town economically dependent on nuclear work. After Monju, the framework operates under scrutiny, yet the assumption persists: low-level waste is inherently manageable. A senior STA official will later note that the 11 March Tokai accident again raised doubts over PNC's capacity to manage nuclear facilities safely, summarizing post-accident commentary from Japanese policy analyses. The statement reflects a pattern: technical competence overshadowed by systemic weakness in management, oversight, and transparency. By the morning of 11 March, Tokai Mura had logged more than 3 decades of nuclear operations. The accident that would redefine its reputation started not in a reactor hall, but in a waste drum. Maintenance personnel stand beside the bituminization extruder in the pre-March 1997 period. A steam-heated screw pushes 180 degrees Celsius bitumen and liquid waste into waiting 180-litre drums. Indicator charts show temperatures within design limits. The process appears straightforward: low-level aqueous waste from reprocessing, rich in sodium nitrate, containing Cs-137, Cs-134, Sr-90, ruthenium isotopes and actinides, is mixed with molten asphalt in the extruder. Water evaporates, generating a viscous slurry. The mixture is poured into steel drum cans on a turntable, allowed to cool naturally, then sealed and moved to storage. Design intent classifies bituminized waste as low-level solid waste, suitable for long-term storage and eventual disposal. The facility incorporates engineered safety features, red zones under negative pressure relative to surroundings, with air routed through high-efficiency filters to prevent spread of radioactive aerosols. Fire protection includes sprinklers and manual hoses. Procedures assume bituminized product will not undergo significant further exothermic reaction if feed ratios and temperatures stay within limits. The process is treated as an industrial chemical operation with nuclear oversight, not as a primary nuclear risk. International experience tells a different story. Earlier European work, including OECD studies on bituminized waste, had identified gas generation, self-heating, and possible runaway chemistries in nitrate-rich bitumen matrices. Japanese technical literature and safety analyses had discussed potential for abnormal reactions in bitumen nitrate mixtures, especially with high salt loadings and inadequate cooling. These warnings remain theoretical, confined to technical journals and specialized meetings. At Tokai, development work seeks higher volume reduction. Between 7 February and 25 April 1997, test runs are planned to improve efficiency. On 11 March, a test using reduced bitumen content is executed. The batch uses approximately 20% less asphalt than normal, increasing the fraction of waste salts in the product. The change is documented in a project schedule sheet listing Improvement of Volume Reduction Rate, Asphalt Reduction Trial. The 11 March run is one in that series. Operators believe they are executing a controlled improvement test. Design and classification decisions, treating bituminization as low-risk conditioning, have shaped staffing, procedures, and emergency imagination. Internal and international literature raised concerns, but facility modifications lag behind understanding. The test moves closer to conditions under which self-heating and gas generation could become significant, without corresponding changes to monitoring, instrumentation, or emergency procedures. On paper, the facility's operating envelope, temperature limits, bitumen waste ratios, maintains a comfortable margin to any exothermic runaway. In practice, the test narrows every safety margin in the room. A post-accident analysis by CNIC will conclude the accident amply demonstrated that there are still a great many uncertainties with regard to the control of chemical reactions at the reprocessing plant, and that serious design faults likely existed in the bituminization facility. The process diagrams show a stable solid. Later, investigators will redraw those diagrams with added arrows, not only heat out, but heat back in. An operator notes in a logbook that the surface of a freshly filled drum appears unusually soft. White smoke starts to rise from the drum surface. The time is approximately 10 o'clock in the morning on 11 March. Conditions not seen in past normal operation now present themselves. Unprecedented softness of product, persistent white smoke. Drums sit in the filling room, positioned close together, with room ventilation set to normal operating parameters. Operating procedures assume that once product leaves the extruder within prescribed temperatures, drum-level reactions will be negligible. The expectation, monotonic cooling with no sustained exotherm. The design basis does not account for ongoing internal heat generation in drums from chemical reactions within the high-salt, low-bitumen matrix. Post-accident modeling will show that product temperatures from the extruder, combined with high nitrate loading and reduced bitumen content, drive continuing reactions even after discharge. Workers later report the abnormal state to investigators. The failure knowledge database summarizes their accounts. The waste fluid solidified with asphalt underwent an unusual chemical reaction, and drums caught fire. At 10:06, flames are observed on a drum during filling. A manual sprinkler valve is opened. Water cascades onto the drum while white smoke rises toward the ceiling. Manual sprinkler use extinguishes visible flames within about 1 minute. The fire appears controlled. Radiation alarms sound. Within 7 minutes of ignition, alarms trigger in rooms where workers are present, rooms not supposed to see contamination from the bituminization line. Smoke drifts through door gaps and service penetrations. Staff in an adjoining low-level liquid waste evaporation facility notice instruments registering activity. The patterns suggest pressure and isolation failures. Airborne dust, smoke and aerosols traverse pathways thought to be isolated, entering spaces assumed clean. Decision-makers classify the situation as fire extinguished rather than ongoing abnormal reaction. Focus shifts to smoke management rather than process forensics. No immediate engineering investigation inside the filling room occurs. The choice reflects how the event is framed: a brief, local fire, now under control, rather than a process excursion requiring full hazard analysis. CNIC will later note that PNC showed poor judgment in assuming that the fire had been successfully extinguished by a manually operated sprinkler, even though the room was still full of smoke. The decision shapes subsequent actions: no immediate assessment of thermal behavior in drums, no verification that exothermic reactions have ceased, no adjustment to ventilation strategy beyond smoke containment. Operators believe the abnormal episode has ended. In hindsight, that moment marked not an ending, but the beginning of a 10-hour countdown. On 11 March, they executed what they thought was a controlled improvement test. The test had quietly narrowed every safety margin in the room, and the room was about to respond. A log entry at 10:06 records fire, observed on drum during filling. A manual sprinkler is activated. Local radiation alarms trigger. Staff in adjacent rooms notice smoke. The decision is made to shut down ventilation fans and close dampers to prevent smoke spread through ducts and doors. The action is intentional, aimed at keeping contamination inside the filling room and preventing migration to adjacent areas. The ventilation concept at Tokai follows standard nuclear practice. Continuous extraction from red zones maintains negative pressure, with air routed through high-efficiency particulate air filters before discharge. This confinement strategy assumes that negative pressure and filtration will operate even in upset conditions, maintaining a barrier between contaminated spaces and the environment. Design documentation does not envision a scenario where ventilation shutdown would be the primary response to fire. Actual practice in this event reverses the logic. Ventilation shutdown reduces smoke migration in the short term, but allows flammable gases to accumulate in a closed room. Drums with high internal temperatures continue to evolve gases, products of ongoing reactions between bitumen, nitrate salts, and residual moisture at elevated temperature. Without airflow to dilute and remove these gases, concentration builds over hours. Post-accident analyses by JEA and JNC reconstruct temperature and gas evolution. High product temperatures from the extruder, combined with high nitrate loading and low bitumen content, drive ongoing gas generation. The failure knowledge database notes that, after the fire, gas generated from the drums accumulated in the filling room over time, leading to a flammable mixture by evening. The chemistry proceeds: nitrate decomposition, volatile organic compounds from bitumen pyrolysis, and combustible gases accumulating in a confined volume. The decision to reduce or stop ventilation is untested against runaway chemistry scenarios. It represents intuitive smoke control, but undermines the intended containment function. The same pipes designed to clear the air stay silent while the mixture in drums keeps reacting. Operators focus on preventing spread. They do not recognize that they are creating conditions for a secondary event far more severe than the initial fire. By late morning, containment performance begins to fail. Rooms handling high-level radioactive materials are red zones under negative pressure to prevent leakage. During and after the fire, this system fails. Contamination is detected in the adjoining low-level liquid waste evaporation facility and other buildings, evidence that pressure differentials and physical barriers are not performing as designed. Airborne activity moves through door gaps, penetrations, or improperly sealed pathways. Workers, not equipped for an ongoing airborne release, move through these areas during fire response and preparation for re-entry. 2 workers escape to a roof area. They will not be rescued for 7 hours. The event is hardly the orderly evacuation PNC will later describe. For almost 10 hours, the filling room remains closed, drums continue to react, and flammable gas concentration rises toward the lower explosive limit. The building's engineered barriers are already not performing as designed, hours before the explosion that will break windows and doors wide open. A telephone rings in a supervisor's office. Staff report that the fire has been extinguished and smoke is still present. The time is late morning. Decisions about next steps are made remotely, based on reports rather than direct observation. No engineer responsible for the bituminization process goes physically to the filling room before the explosion 10 hours later. PNC internal organization includes on-shift supervisors, off-site technical experts, and escalation protocols that exist on paper. Procedures expect technical staff to confirm abnormal events and verify safe conditions before resuming normal work. In reality, the event is treated as minor. Focus shifts to resumption planning, rather than in-depth forensic assessment of abnormal process. Indicators: soft product, white smoke, persistent alarms. The absence of engineering presence and rigorous hazard analysis shapes what happens next. The process line remains shut, but the building is being readied for worker access. Ventilation status in this period allows thermal behavior of sealed drums to continue unchecked. Modeling that will be conducted months later shows temperature and gas generation remaining elevated for many hours. Drums in the closed filling room experience self-heating. Exothermic reactions in the high salt, low bitumen matrix generate heat faster than it can dissipate by natural convection and radiation to room air. Internal temperatures rise. Gas generation accelerates. Several tens of workers are scheduled to re-enter the building. Preparations proceed on the assumption that the fire is fully extinguished and hazards have subsided. An online ethics teaching case will later highlight this moment. The explosion occurs approximately 40 minutes before the planned inspection. Had the timing been slightly different, many workers could have been inside the building during the blast. Luck, not procedure, prevents a near-miss mass casualty event. The decision to plan re-entry without comprehensive technical assessment reflects a broader pattern. The event is framed as a brief equipment upset rather than a potential ongoing chemical hazard. This framing flows from design classification, bituminization as low-risk, low-level waste conditioning, and from institutional pressures to minimize disruption and resume operations. The mindset: fires are extinguished with water. Once flames are gone, the problem is solved. Contrast this with what investigators will later determine should have occurred. Immediate process engineering review, thermal imaging or thermocouple measurements of drum surfaces, continuous gas monitoring in the filling room, and a formal hazard analysis before any re-entry. None of these steps are taken. The gap between what safety analysis presumes and what actually happens in an upset grows wider with each passing hour. By mid-afternoon, the building remains nominally under control. Radiation levels in adjacent rooms have stabilized at elevated but manageable values. Smoke has largely cleared from visual observation points. On paper, conditions appear to be trending toward normal. Inside the filling room, sealed from view and from ventilation, the drums continue their invisible transformation. Solid waste becoming a gas-filled bomb. In a neighboring low-level waste facility, staff hear intermittent radiation alarms. Their location lies outside the BDF red zone, but airborne activity begins to register on monitors. The time is midday to late afternoon on 11 March. The pattern of alarms indicates that containment has been compromised beyond the filling room itself. The concept of red zones relies on compartments under negative pressure, designed to keep airborne contamination confined. Air is continuously extracted through high-efficiency filters, maintaining a pressure differential that prevents leakage from contaminated spaces to clean areas. The system is engineered so that any breach, an open door, a failed seal, results in airflow into, not out of, the hazardous zone. This principle is fundamental to nuclear facility design. Shutting down fans and closing dampers to contain smoke reverses this logic. Without continuous extraction, pressure differentials collapse. Doors that rely on negative pressure to maintain seals now leak. Penetrations for pipes, cables, and ducts, normally protected by differential pressure, become pathways for contaminated air. The decision aimed at short-term smoke control has undermined the facility's primary confinement strategy. Airborne monitors and smear tests later record contamination in areas that should have remained clean. The pattern demonstrates a systems-level failure. Engineered barriers, assumed robust in design analyses, perform poorly when operating conditions deviate from assumptions. Exposure levels at this stage are still low, background plus a small increment, but the breach is real. Contamination outside intended confinement complicates later cleanup and monitoring, and signals that control has been lost at a fundamental level. The Science and Technology Agency's Survey Committee will later meet more than 30 times to reconstruct these barrier failures. Recommendations include tighter control of ventilation interlocks, redesign of pressure monitoring systems, and revised emergency procedures that maintain confinement even during fire response. The committee's work underscores a key lesson. In nuclear facilities, fire response tactics borrowed from conventional industry can conflict with radiological confinement principles. Workers moving through adjacent buildings during this period are not equipped for ongoing airborne release. Standard practice assumes that if alarms sound, contamination is brief and localized. Continuous low-level release over hours is outside the expected scenario. Some workers receive small internal intakes during this phase, intakes that will be detected days later during whole-body counting, but that go unnoticed in real time. Decisions aimed at containing smoke in one room lead to contamination spreading through unexpected pathways. The mismatch between design intent and observed behavior grows starker. By late afternoon, the building's engineered barriers, negative pressure, filtered ventilation, sealed penetrations, have failed to confine activity as designed. The facility is no longer operating within its safety basis. Inside the filling room, drums that had smoldered for hours sit amid residual smoke. Flammable gases, generated by high-temperature asphalt salt reactions, have accumulated in the confined space. Concentration approaches the lower explosive limit. All that remains is an ignition source. At 8 o'clock that evening, ignition occurs. Inside the filling room at approximately 8 o'clock in the evening on 11 March, drums sit in partial darkness. Ventilation has been off for hours. Gas concentration has built steadily. Volatile organics from bitumen degradation, nitrogen oxides from nitrate decomposition, combustible mixtures at temperatures elevated by ongoing exothermic reactions. The room has become a closed vessel primed for deflagration. Ignition occurs. The source is uncertain. A hot surface, a static spark, residual embers. But the result is immediate. Flame propagates through the gas mixture. Pressure rises rapidly. The explosion is not nuclear but chemical, a dust and gas deflagration driven by accumulated fuel vapor. The blast wave moves outward, seeking paths of least resistance. Physical effects are severe. Explosion pressure breaks doors and windows, damages roofs and equipment, and creates direct openings from the contaminated interior to outside air. The thick lead door separating the filling room from adjacent spaces is destroyed. Window panes shatter, roof panels buckle. The failure knowledge database describes structural damage. As a result of this explosion, the radioactive material was discharged to the environment from openings such as windows. Post-accident investigations by Omori, Hasegawa, and others reconstruct the event. Several drums likely catch fire again after the explosion and burn until fuel is exhausted. Modeling identifies self-heating and gas generation in bitumen nitrate mixtures as key drivers. The chemistry that seemed stable on process flow diagrams has revealed its instability under real-world conditions, variable feed composition, temperature excursions, inadequate monitoring. Human consequences are immediate. Some workers end up on a roof area. They will be rescued only about 7 hours later, according to CNIC reporting. Additional alarms trigger across the facility. Emergency procedures activate belatedly. The order to evacuate all workers from affected buildings is issued roughly 30 minutes after the explosion. The timing underscores the reactive rather than proactive nature of emergency response. The explosion nearly coincides with planned worker re-entry. An online ethics case summary notes. Later, as workers were just about to enter the room to investigate the fire damage, the explosion occurred. Only luck prevented them from being caught in the blast. The 10-hour gap between fire and explosion, combined with decisions to prepare for inspection, created the risk that many more workers could have been directly exposed. The scenario transforms from fire under control to near-miss mass casualty event. Radioactive material, cesium isotopes, strontium, ruthenium, and traces of actinides, escapes through breached barriers. The explosion aerosolizes contamination that had been confined to drums and surfaces, creating a plume that disperses through broken windows and damaged roof sections. Environmental monitoring will later detect this release at distances of 16 to 60 kilometers from the facility. The blast marks the transition from contained upset to uncontrolled release. Everything that follows, exposure assessments, environmental surveys, regulatory investigations, institutional consequences, stems from this moment. The explosion did not change the chemistry or the design flaws. It merely revealed them in a form that could not be minimized or explained away. A temporary monitoring line is set up on 11 and 12 March. Workers who are in and around the facility queue for whole body counting and thyroid checks. The process is methodical. Each worker enters a shielded chamber, sits still for several minutes while detectors measure gamma emissions from any internalized radionuclides. Thyroid probes check specifically for iodine isotopes, which concentrate in that organ. Results emerge over hours and days. 129 workers undergo examination. 37 show internal contamination, mainly with cesium isotopes, Cs-137 and Cs-134. PNCs released whole-body counter data indicate maximum internal contamination of approximately 2,700 becquerels of Cs-137 and 400 becquerels of Cs-134 in individual workers. PNC evaluates these levels as about 1 over 2,100 of the annual intake limit, a small fraction of regulatory thresholds. The numbers are small, but the pattern is unprecedented. CNIC's analysis concludes this was the highest number of workers ever exposed in one accident, and the longest period ever, in which radiation has been allowed to leak to the outside environment in Japan's nuclear history up to that point. The statistic, 37 internally contaminated, becomes a defining measure of the accident, more potent in public discourse than the actual dose figures. Dose units require context. Committed effective doses for the exposed workers are estimated in the range of 0.1 to a few millisieverts, equivalent to roughly 0.01 to 0.3 rem. These values fall well below occupational limits and are comparable to or less than a typical chest X-ray or a few months of natural background radiation. No acute radiation injuries occur. No worker experiences symptoms attributable to radiation exposure. Yet the event represents a qualitative break. Previous Japanese nuclear incidents involved smaller numbers of workers, shorter exposure windows, or more contained releases. The Tokai explosion created a scenario where dozens of workers inhaled or ingested radioactive material over an extended period in a facility classified as low risk. The mismatch between facility classification and actual outcome drives both regulatory concern and public alarm. Environmental monitoring begins immediately. Early sampling shows low-level activity in air filters and surface dust around the facility. On-site contamination is measurable. Off-site, contamination in food or water is not initially detected. PNC statements emphasize that doses are well below limits and that no harm has occurred, framing the event as minor. The messaging focuses on numerical thresholds. Exposures are legal, therefore acceptable. Independent assessments take a different view. CNIC argues that PNC's dose estimates, based only on cesium, understate total risk. Other nuclides, ruthenium, iodine-129, americium, plutonium, should be considered. CNIC's own analysis suggests that total effective dose could be substantially higher than PNC's cesium-only estimate, though still below intervention levels. The Science and Technology Agency assigns the event an International Nuclear and Radiological Event Scale Level 3 rating, Serious Incident. The classification clashes with early claims of trivial impact. Level 3 indicates an event with very small release of radioactive material, exposure of workers above statutory limits, or incidents with significant safety implications. Tokai meets multiple criteria. By the time off-site monitors detect elevated cesium in air 60 kilometers away, PNC is still publicly describing the event as a small increase within safety limits. The gap between official messaging and independent measurement sets the stage for the next phase: revisions, reassessments, and the erosion of institutional credibility. In Tokyo, Science and Technology Agency officials go about normal work on 11 March. No urgent fax or phone call arrives from Tokai in the hours after the morning fire. The STA duty log for 11 March shows routine entries: reactor status, environmental monitoring, ongoing policy discussions. The first detailed information about radiation release and worker exposure appears only in the afternoon and evening, hours after PNC management was fully aware of events. Regulatory requirements mandate immediate notification of significant nuclear incidents, fires involving radioactive material, unplanned releases, worker exposures above thresholds. PNC's behaviour falls short. Although the report of the fire is relatively fast, it takes more than 3 hours for information about the radiation leak and radiation exposure to be reported, even though PNC is fully aware. The delay is not accidental. It reflects institutional priorities. Documentation later reveals that PNC management instructed 2 workers to report a falsified sequence of events leading to evacuation, attempting to conceal inadequate supervision and decision-making. The falsification aims to obscure who made key decisions, when those decisions were made, and what information was available at the time. The motive: protect management from accountability for procedural failures. The pattern echoes Monju. After the 1995 sodium leak, PNC delayed notification to authorities, edited surveillance video to minimize apparent severity, and issued public statements that understated the event's significance. Post-Monju reforms were supposed to ensure rapid, transparent reporting of any significant nuclear incident. Practice at Tokai shows continued reluctance to promptly reveal severity once radiological release and internal exposures are known. Delayed, partial reporting impedes STA's ability to coordinate external monitoring and emergency assessment. Independent meteorological stations at Tsukuba, 60 kilometers southwest, and Mito, 16 kilometers southwest, detect abnormal airborne cesium levels days after the explosion. The detections come from routine environmental surveillance, not from PNC notifications or STA emergency response. The agencies learn about off-site contamination from external data, not from the operator. The notification failure compounds physical consequences with institutional damage. Public trust, already fragile after Monju, erodes further. Politicians and analysts criticize PNC's delay, describing it as incompatible with public safety obligations. When STA finally pieces together the full sequence of events, the gap is not only in time, but in truth. The 5-hour silence between initial awareness and full disclosure becomes a symbol. It demonstrates that despite reforms and assurances, the institutional reflex remains: control the narrative, minimize the appearance of severity, protect the organization. The strategy backfires. Each revelation of delay or falsification amplifies the story, turning a numerically modest release into a credibility crisis. Later commentary from Japanese policy analyses frames the Tokai accident in terms of safety culture, not accident physics. The problem is not that the release was large, it wasn't, but that the organization's response revealed systemic inability to acknowledge and communicate risk transparently. The numbers: 37 exposed workers, 5 hours of silence, falsified evacuation timeline, become the narrative. The accident again raised doubts over PNC's capacity to manage nuclear facilities safely, as a senior STA official notes. The phrase is diplomatic, but the implication is clear. Competence is not enough if transparency and accountability are absent. The Tokai fire did not produce high doses, but it produced a documented case study in how institutions fail. A press briefing room in Tokyo, late March 1997. PNC officials present an early estimate. Radiation levels around the plant rose by about 20% compared with normal. Reporters note the figure. The number is reassuring, suggesting a minor perturbation, well within the envelope of natural variation and regulatory margins. The 20% figure appears in early media coverage, shaping public perception of the event's scale. Revisions follow. As independent measurements accumulate, and as STA presses for supporting data, PNC acknowledges that peak readings had been around 10 times higher than first stated. The discrepancy, 20% versus tenfold. Increase is stark. It raises immediate questions. Was the initial estimate an error or an attempt to minimize? Independent analyses provide context. Using measured air concentrations at Tsukuba and Mito, INES estimates total beta releases in the range of 1 × 10 to the 9th to 1 × 10 to the 10th becquerels, with alpha releases around 1 × 10 to the 7th becquerels. These values translate to roughly 0.03 to 0.3 curies of beta-emitting radionuclides, dominated by cesium. PNC's own estimate for released activity is on the order of 5.8 × 10 to the 7th becquerels beta, including 2.13 × 10 to the 6th becquerels of iodine-129 and 2.2 × 10 to the 4th becquerels alpha. When asked for the calculation basis, PNC says it is not prepared to provide one as of early April. Units require explanation. 1 becquerel equals 1 radioactive decay per second. 1 curie equals approximately 3.7 × 10 to the 10th becquerels. The Tokai release, estimated at 1 × 10 to the 10th becquerels, or 0.3 curies, is orders of magnitude lower than major reactor accidents. Chernobyl released roughly 10 to the 18th becquerels. 3 Mile Island, roughly 10 to the 15th becquerels. Yet for a low-level waste conditioning facility, 0.3 curies is significant. It produces measurable off-site signals and requires environmental follow-up. Normal cesium-137 concentration in air at Tsukuba averages approximately 1 × 10 to the -6th becquerels per cubic meter. Detected after the explosion, 84 × 10 to the -6th becquerels per cubic meter of Cs-137 and 13 × 10 to the -6th becquerels per cubic meter of Cs-134, roughly 80 times normal for cesium-137. At Mito, 16 kilometers southwest, Cs-137 in air reaches 41 to 600 times 10 to the -6th becquerels per cubic meter, up to 600 times normal. The numbers tell a story. PNC's public narrative stressed low doses and minimal release. Independent estimates and later official documents indicate higher peak levels and broader dispersion than first admitted. The debate shifts from how big was the release to why were the first numbers so incomplete. CNIC's analysis concludes that PNC's data are insufficient for an independent analysis and criticizes the statement there is no effect to the surrounding environment as unsupported by evidence. The evolving release figures drive calls for external investigation and help frame Tokai as a matter of safety culture, not just accident physics. Measured in becquerels, the release is modest. Measured in revisions and inconsistencies, the damage is substantial. In the end, the most damaging release from Tokai is not a nuclide, it is confidence in the official numbers. At the Meteorological Research Institute in Tsukuba, 60 kilometers southwest of Tokai, an air filter sample from 18 March shows cesium-137 levels roughly 80 times normal background. Technicians check their instruments, run calibration standards, and confirm the reading. The sample is from routine environmental surveillance, unrelated to PNC's emergency response. The detection is independent, unannounced, and unambiguous. Normal Cs-137 concentration at Tsukuba averages approximately 1 × 10 to the -6th becquerels per cubic meter, reflecting global fallout from atmospheric weapons tests in prior decades. The 18 March sample, 84 × 10 to the -6th becquerels per cubic meter of Cs-137 and 13 × 10 to the -6th becquerels per cubic meter of Cs-134. At Mito, 16 kilometers southwest of Tokai, Cs-137 in air reaches 41 to 600 times 10 to the -6th becquerels per cubic meter during the same period. The detections confirm off-site dispersion. Explosion-generated aerosols carried by prevailing winds have dispersed across the Kanto region. Cesium-134 and Cesium-137, with half-lives of approximately 2 years and 30 years respectively, serve as tracers. Their ratio indicates the source, fresh fission products from reprocessing waste, not age fallout. The signature is distinct. Other surveys find low-level contamination on site in soil and surfaces. However, food, water, and most environmental samples outside the site remain within normal variation, according to IAEA and Japanese reports. The release, while measurable at distance, does not produce intervention-level contamination in crops, drinking water, or foodstuffs. Long-term monitoring confirms this pattern. No chronic dose pathway to the public emerges from the 11 March event. Dose assessment proceeds. Official and independent evaluations conclude that public doses from the Tokai 1997 accident are far below intervention levels and substantially below common medical exposures. A chest X-ray delivers roughly 0.1 millisievert, a CT scan, several millisieverts, annual natural background in Japan, approximately 1 to 2 millisieverts. Estimated doses to the maximally exposed individual downwind of Tokai are fractions of these values, micar millisieverts, not millisieverts. Occupational doses, while low, represent an unprecedented number of workers with internal contamination in a single Japanese nuclear incident, 37. The contrast is stark. Physically, Tokai 1997 does not impose significant radiological risk on the general public. Socially, measured off-site activity plus earlier minimization by PNC amplifies public concern, especially in a region already wary after Monju. International analyses of the Tokai accidents, 1997 and the 1999 JCO criticality, later highlight human error and serious breaches of safety principles as central causes, not extreme source, terms. The IAEA and OECD summaries echo this message. The accidents are organizational and procedural failures, not physics-driven catastrophes. The releases are small, the doses low, yet the events expose systemic weaknesses in oversight, training, and safety culture. The mismatch between modest dose estimates and highly visible monitoring anomalies sets the stage for rethinking how low-level facilities are regulated and communicated about. If a conditioning line for low-level waste can expose 37 workers and produce detectable activity 60 kilometers away, what does low-level mean? The term implies benign, routine, minimal hazard. Tokai demonstrates that classification is not destiny. Process chemistry, operating conditions, and human decisions determine outcomes. The final dose maps stay reassuringly pale. No red zones off-site, no evacuation thresholds crossed, no long-term dose commitments above background variation. The final policy documents do not. They call for redesign, re-evaluation, and regulatory reform. A public meeting in Tokai Mura, late 1990s. Residents hold banners referring to Donan accidents, using the Japanese abbreviation for PNC, Doryokuro Kakunenryo Kaihatsu Jigyodan, and linking the 1997 Tokai fire with broader grievances against the nuclear establishment. The mood is skeptical, the questions pointed. Residents demand criminal prosecution of PNC officials, leadership changes, and closure of the reprocessing plant. Local reaction reflects accumulated frustration. Monju's sodium leak and cover-up in 1995, followed 2 years later by Tokai's explosion and exposure of 37 workers. Each incident featured delayed notification, data manipulation, and institutional defensiveness. Trust, once eroded, proves difficult to restore. Tokai Mura, economically dependent on nuclear facilities, finds itself questioning whether the benefits justify the risks. National policy response includes institutional reorganization. PNC is restructured into the Japan Nuclear Cycle Development Institute in October 1998, and later JNC merges into the Japan Atomic Energy Agency in 2005. The reorganizations aim to reset governance, improve transparency, and restore credibility after Monju and Tokai. Whether the changes represent substantive reform or cosmetic rebranding remains debated. The 1999 JCO criticality accident at another Tokai area facility reinforces international perceptions of inadequate safety culture and regulatory oversight in Japan's fuel cycle sector. On 30 September 1999, workers at the JCO uranium conversion plant in Tokai Mura bypassed procedural controls, manually mixing uranium solution in buckets, and trigger Japan's first criticality accident. 2 workers receive lethal doses. Hundreds are exposed to neutron radiation. The accident, classified INES Level 4, confirms that systemic issues persist beyond individual facility failures. OECD Nuclear Energy Agency and IAEA documents begin to cite Tokai 1997 alongside Monju and JCO as case studies in organizational failure. The pattern is clear. Japan's nuclear engineers have accumulated substantial technical achievements, advanced reactors, fuel reprocessing, plutonium handling, yet repeated accidents, notification delays, and data handling issues signal systemic weakness in management, oversight, and transparency. Tokai 1997 becomes part of the chain of documented events that drive later reforms in Japanese nuclear regulation and emergency planning. The Nuclear and Industrial Safety Agency is separated from the Ministry of Economy, Trade and Industry to reduce regulatory capture. Emergency planning zones are expanded. Public communication protocols are revised. Whether these reforms prove sufficient will be tested in March 2011, when the Fukushima Daiichi accident exposes further gaps. Before Fukushima made reactor names globally familiar, Tokai had already taught regulators that the weakest point in a fuel cycle can be an office, not a core. The lesson? Technical systems are only as reliable as the institutions that operate them. Design margins, engineered barriers, and procedural controls all depend on organizations willing to acknowledge uncertainty, report problems promptly, and prioritize safety over reputation. The Tokai fire did not produce the dramatic imagery of a reactor accident. No hydrogen explosions, no evacuated cities, no exclusion zones. Yet it revealed dynamics that would recur: institutional reluctance to disclose bad news, delayed notification undermining emergency response, and the gap between engineering competence and organizational integrity. The 37 exposed workers, the 5-hour notification delay, the tenfold revision of release estimates. These numbers define Tokai's legacy more than any dose calculation. An OECD Nuclear Energy Agency workshop slide lists bituminized waste incidents, several European cases, an American near-miss, and PNC Tokai Works, 11 March 1997, highlighted as a major reference point. The event joins a small but significant set of accidents demonstrating that radioactive waste solidification is not inherently benign. OECD, NEA and IAEA documents after 1997 increasingly emphasize rigorous process control for bituminization. Guidance includes detailed characterization of nitrate-bearing wastes before treatment, strict control of feed composition, especially salt content and bitumen waste ratios, continuous or improved monitoring of product temperatures and off-gas, and ventilation systems designed to cope with smoldering or gas-generating scenarios without sacrificing containment. Some national programs reduce or abandon bituminization in favor of cementation or alternative matrices for specific waste streams. The shift reflects lessons learned. Nitrate salts in bitumen create a metastable system. Under normal conditions, moderate temperature, adequate dilution, good mixing, the product is stable. Under off-normal conditions, high temperature, high salt loading, poor heat removal, exothermic reactions can self-accelerate. Gas generation follows. Nitrogen oxides, volatile organics, combustible mixtures. If confinement and ventilation fail, fire or explosion becomes credible. Technical reconstructions at Tokai identify contributing factors. Koyama, Sato, Omori, Hasegawa, and others publish analyses in the years following the accident. Key findings: internal heating in the extruder, raised product temperature beyond design assumptions, reduced bitumen content in the test batch, increased salt loading and reaction susceptibility. Drums in the filling room experienced further self-heating as residual reactions continued. Inadequate ventilation allowed gas accumulation. An explosion occurred when flammable mixture reached ignition conditions. Experiments on asphalt salt mixtures quantify explosion thresholds and reaction kinetics. The work provides data that were absent from original design analyses. It also validates concerns raised in earlier international literature. Bituminized nitrate wastes require careful thermal management and cannot be treated as inert. Japan's response includes extended shutdown of the bituminization facility at Tokai and redesign of waste treatment systems. Safety countermeasure groups and STA survey committees recommend changes: temperature monitoring at multiple points in the process, gas detection and analysis in the filling room, ventilation interlocks that maintain containment even during upset conditions, revised procedures for abnormal events, including criteria for engineering review before resuming operations, an updated safety analysis addressing fire, explosion, and radionuclide release scenarios. Long-term monitoring around Tokai does not identify significant chronic dose to the public attributable to the 1997 accident. Environmental surveys, soil sampling, and food chain studies show no measurable increase in long-term exposure. The event's radiological impact, measured in sieverts and population dose, is negligible. Its impact on waste management practice and nuclear safety culture is substantial. Originally classified as a low-level waste conditioning process, Tokai's bituminization line is now cited internationally as a process requiring a high level of safety analysis and control, comparable in seriousness to higher-profile nuclear systems. The reclassification reflects a broader understanding. Low-level describes radionuclide inventory, not process hazard. A facility handling low-activity waste can still present significant chemical, fire, or explosion risk if process chemistry is poorly understood or inadequately controlled. CNIC's March-April 1997 article concluded that Tokai had revealed basic design fault in the bituminization facility and significant uncertainty in controlling reprocessing cycle chemistry. IAEA and OECD summaries later echo that message. Human factors and process safety weaknesses, not reactor physics, dominated risk at Tokai. A single low-level waste accident influenced global practice in bituminization safety and, more broadly, attitudes towards secondary nuclear systems. Measured in becquerels, the Tokai release was small. Measured in procedures rewritten, facilities redesigned, and agencies reorganized, it was one of the most consequential low-level waste accidents in nuclear history. 11. March 1997 at Tokai did not produce high public doses, but it produced one of the clearest demonstrations that even low-level waste lines must be treated as potential nuclear hazards, measured in both becquerels and in trust.